demo later on, and then that might stimulate some questions from the audience. I'll put the robot down. I'll put it here for now. So those are the kind of aims of the presentation. I'll start off with a little bit about me as an engineer, okay? Because I'm definitely the oldest person in the room today. So I've had quite a long career. I started off in BA Systems and had some opportunities to look at do some really interesting projects. I worked on making satellite dishes. So the satellite dishes was about 2 meters in diameter. And the ones I was working on, they were shaped, okay? So if you've just got a parabolic reflector, then you'll get a certain parabolic shape, on the ground, there's things in space. So that's where your footprint will be. But if you put dents in it, then you can change the shape on the ground. So then you can make sure that you're not putting energy into the sea as opposed to into the land, okay? And my role was these shaped reflectors had an aluminium coating, and because it was a Polaroid reflector, we needed to cut lines into the aluminium. So we had a gantry system which had a working area of about 3 meters cubed. We had a massive laser on the side, which would then pulse laser light with a mirror system, which would come down the arm and then hit the aluminium and ablate it. So we could move the arm and then put stripes into the aluminium. And my role was to they had a slight control problem where the arm wasn't being controlled very well, so it was going too high or too low, and then the thickness of the lines were getting too close together or too far apart. And I put some control mechanisms in there to get the lines nice and parallel. But it's quite nice to think of something that you've made. These were made out of Kevlar. It's quite nice to think of things that you've made actually making it into space, and allowing people to communicate. This was for a communication satellite. So that was great. Another piece of work, I was doing my research in Bristol. I was working with a guy from Oxford University, and I was working for an aerospace company. And all my the stakeholders who came to see my work, I was demonstrating them on little robots, in the lab, and they actually wanted to see things fly in the air. But actually, in the UK, getting access to airspace is really tricky. So my colleague from Oxford took a chair in Sydney University, and then he phoned me up and he said, or in fact sent me an email, and he said, look, I'm at Sydney University, and about 100 kilometres north of Sydney, there's an area where they do research into sheep. They don't care what you fly there. Okay, so I got on the plane, went over to Sydney, got the mechanical engineers. We went down to their equivalent of B&Q. We got a drain pipe, we got some balsa woods, and then we were able to put together one of these kind of UAVs and unmanned air vehicles. So again, I could, we made 4 of these, and then I could demonstrate some of my decentralized algorithms with things that were actually flying, which was a great project. In the year 2000, I was going to become a multi-millionaire. It was the dot-com boom. So I decided, right, I'm going to go out and make my fortune. So I moved into the microelectronic industry. I went to a startup company called Super H. And we thought, right, we've got this core processor, we can sell it to lots of people. There was like a little company called ARM, who was our competitor. We were about the same size at the time. Of course, ARM have gone on to do great things, and Super H kind of dived. But I stayed in the microelectronic industry, even though the startup finished. And I ended up working in ST Microelectronics, making system-on-chip devices to go into your set-top boxes, your Sky boxes and things like that. And the last part that I built sold over 12 million parts. So it's again quite nice to think of things that you've made, contributing to people, entertainment and things. My career as well, I've had lots of opportunity to travel around. So I've been to lots of places in the US, MIT and places like that. I've been to Sydney, as I mentioned, Atlanta. I've been to Jerusalem, lots of different places. So I've really enjoyed traveling and meeting new people from around the world. And also through my work, I've worked for three companies, met lots of people through that. I'm involved with lots of institutions and things as well, which is another great way of meeting interesting people. And I've got some good associations with different universities. Also, as mentioned, in about 2017, I had the Royal Academy of Engineering gave me some money. They've got a scheme to try and get people with grey hair, like myself, to come and talk to students at universities. So I took on that role with Imperial College in London. And then, some of the academics said, Rob does a lecture on robotics, and then other people were asking, for the lecture as well. So it's expanded in the UK. And then we went into lockdown, and then some of my associates from around the world were also asking for online lectures. So I did a bit of online lecturing. So it's great to have, started to cover the globe with talking about robotics, which has been great fun. So thank you to Dyson, who allowed me to do that, the Royal Academy of Engineering, who provided me with some funding, Imperial College, which gave me a base to work from, and also the University of Birmingham for their honorary professorships. Okay, so that was just a little bit about me as an engineer. I'll now go on to the kind of the meat of the lecture, which is to talk about robots in the home. And primarily I'm going to look at the work that Dyson has been doing over the last 20 years ago. So the story started with the DC-06. So Dyson wanted to get into robotics. So they brought some guys from the University of Kent and brought them over to Dyson to develop robotics. And the first robot that was nearly launched, it wasn't actually launched, was the DC-06. So it was quite a big robot, quite heavy, quite complex, had lots of electronics boards inside it. And then at the last minute, it was decided not to launch that robot and to kind of start again, effectively. So that they went on we eventually launched the first robot, the 360i, in 2014, just when I joined the company, actually, which was great achievements to get the robot out. We then moved on to do the 360 Hurist, so they asked me to be the technical lead for that robotic development. They said, look, we're only going to do a few changes to the robot. Of course, we changed all the electronic boards in there, so it was a bigger task than originally thought. One of the main things that came out of it, the 360i, it would build a map of your environment when it was doing its cleaning. And then at the end of the clean, it would throw it out and wouldn't reuse it, okay? So we thought that was a bit of a waste of information, effectively. So with a 360 Hurist, what we were able to do was we would keep the map, and then we would share it with the user, and then they could use it. So they could partition, you'd get kind of an estate agent's view of your floor area, and then with an app you could then Dyson slice it into different bits, call that the living room, call that the hallway and stuff. So you could, and then you could reuse the map effectively. So that was the big step up from the 360i to the 360 Hurist. There was loads of other things. There was much more processing on it. We changed the camera system and the illumination and stuff. But one of the main features for the user was the fact that we could reuse the map and they had more control effectively. And then in 2023, last year, we launched the 360 VisNav, and I've brought one with me. I'll have it running around later on. So this is now the first robot which has got a full stick vac cleaning system in it. Or the previous robots, the cleaning systems weren't quite as powerful as the stick vac, but this one's got a cleaning system that is comparable to our stick vac technology. So that's just a bit of an overview of the roadmap so far for Dyson Robotics. We're all roboticists thinking about the robotic elements of things, but if you're to make a commercial product, then you have to, generally you need to have a payload, okay, so that the robot actually does something for you, and the payload that we've got is a cleaning system, and that payload will quite often affect your robotics as well, okay? For our cleaning system, because we're gathering bits of dirt in inside a plastic bin, then we get lots of static electricity, so that can, again, affect the performance of the system. I'll just give you a quick overview of how the cleaning system works. It all starts with the agitation, okay, so that's the kind of this brush bar under here. So on this robot, there's a 50-watt motor which rotates this, and then that agitates the dirt in the floor. It's got 3 different components to it. It's got this kind of fluffy stuff here, which is really good. So if you've got like things like Cheerios or big bits of debris, then with the fluffy, it goes over it without losing suction, because it kind of, it's compliant around the debris, and then it can pick it up really easily. We've got these kind of red bristles here, and later on you can come down and feel them. They're quite stiff, okay, and they're really good on carpet in beating the dust out of carpet. Okay, so that's what they're for. And then we've got these, and then the third element is these black bristles are much finer and softer, and they're really good at gathering dust on hard floor. Okay, so we've got those 3 different elements to the brush bar. Now even that bit takes a lot of design, right? Because if I make the red hard bristles too stiff and too long, then when I run it on my hard floor, I'm going to scratch it. Okay, so all these things need to be taken into account when you're putting a robot together. There's also on this robot a side edge device as well. So when the robot has finished cleaning the main part of your room, it'll then the side edge actuator will pop out, and then it'll go around the edge of your room to gather the dirt from the close to the edge by your skirting boards and things like that. So that's the kind of agitation part. Once you've got the so you've agitated your dirt, so you've got this dirt now with a bit of air, you've got this air with bits of dirt in it. You then need to pull it through the system. So for that, we've got we need to get an airflow, and for that we've got a vacuum motor. And the one we've got here is a V10, which is a 400-watt electrical power motor. So it's quite a powerful motor, and then that gives you an airflow through the system. Okay, so we've agitated the dirt. The next thing to do is to try and separate the dirt from the air. Okay, and for that we've got a separation system that also acts as a bin. So what happens is that the air with the dirt comes in through this hole, okay, because it's been pulled in through the vac motor. It spins around the outside, and then all the big bits of dirt are pushed out to the outside, and then they drop into this part of the bin. The remaining air go through the cyclone system, and the cyclone system is basically 8 cones, okay, with the small part of the cone at the bottom. Well, I'm not sure if you can see it, but later on you can have a look. You can see the bottom of the cones here. The top of the cones are here. So what happens now is we've taken the big bits of dirt out, and then you've still got small bits of dust in the air. So now it's going around these kind of cones, and again spinning very, very quickly, and then it pushes the small bits of dust to the edge of the cone, and then the dust then falls down into the bottom part of the central part of the bin. Okay, so that's the separation system. The air then continues over the motor. So in order to avoid bits going into the motor, we've got a filter system. It's nice and convenient in the robot. You can just pull it out. This is the filter. So what happens is the air is pushed in through the filter before it goes over the motor, and then it's pushed back through the filter before we push it out into the open air, so that we don't let any bits of dust go into the environment. So that's the filter, and it pops into the robot like that. The other thing that was really good, myself, I love this because there's a little catch here, which I won't open it here because there's a bit of dust in there. But if I open it, then the bottom falls out, all the dust falls out, and the bin opens. With the previous version, you had to, on the Hurist, for example, you had to take the bin apart, and then you had to tap it on the side of the bin to get the dust out. Sometimes you'd have to put your finger in and stuff, which wasn't very pleasant. So with this bin, it's much more convenient to get the dirt out. Okay, so that's just a very quick overview of a cleaning system. So I'm sure you didn't think this morning when you got up you'd be learning about cleaning system in a robotic conference. But anyway, that was what we've got for the cleaning system. I'll now quickly look at the power system. So the robot has it's about a 98 watt-hour battery in it. And it'll run in auto mode for about 40 minutes. In auto mode, the robot will decide on what cleaning mode it needs, depending on the dirt it's picking up. It's got a dirt sensor inside, and I'll say a little bit more about that later on. We went for a split battery pack. Okay, so we've got two parts of the battery pack, and they're connected by a buzz bar. A buzz bar, just a thick cable. Effectively. And the reason that we've got a split battery pack is that we wanted to get nice balance in the robot. Okay, we found it quite difficult to fit everything together if we just had a big battery pack. So we ended up splitting the battery pack to give us a bit of balance. The robot will go out and do a clean, and then it'll come back to get a recharge if it needs to. So for the charging system, we've got two charge contacts on the front here. You can see them here, just two metal parts. And then the robot will drive onto the dock and then make contact. And then there's also an interlock on the dock, a switch basically. So when it detects that the robot is engaged, then it'll start charging the robot. You can see on the slide there, on the dock, there's two fiducials, the kind of black and white squares. The robot has got an upward-facing camera, and it'll search for these fiducials for fine alignment when it's getting onto the dock, and uses that to get good contact for charging. For the dock, we've got a PSU which is outside of the dock, so you can plug it into the wall wherever where it's convenient in your house. And then there's a cable that will take it to the dock. You can connect it from either side of the dock as well, which makes it more convenient for the user. When you're charging the battery, it's a bit piecewise linear. So you can charge quite quickly to start with the battery, and then it takes longer to charge the end bit. From 80% onwards, it takes longer to charge the battery. So we've got two charging modes. When we come back to the dock after finishing a clean, we will charge it to 100%, which takes takes a reasonable amount of time. But if we're doing a mid-clean recharge, okay, so if we've decided that actually we haven't finished the clean, but we need more charge, we will go back to the dock and then top it up. But we won't go to the 100% because we've got data for how many users use a second clean to finish the cleaning their home, then we can decide what the optimum point is for charging for the second clean for most of our customers. So that's how we do the recharging. Another important part of the robot is the user interaction with the robot, and we've got three parts for this. We've got on board, we've got kind of the home network type stuff, and we've also got the app as well. Okay, so on the first couple of robots, the first robot, in fact, the 360i, we thought we could get away with just a button. We would just push it and then it would go clean and come back. But we suddenly realised that we needed to give some information to the user. So we just introduced some LEDs basically, which is a bit tricky. It's almost like having a binary number that you need to decode into. Oh, that's the brush bar. That's stuck or something. So on the 360 here is the second robot. What we did was we put little icons inside the plastic, so that you had a little icon that represented the Wi-Fi connectivity, for example. And then we then progressed that even further on the 360 VisNav to include an OLED display. It's also got a touch capability and a button, which is great because for you can swipe, go through menus and things. So you've got quite good control just on the robot. It's got a great setup as well. So you can either start the robot from the dock, but you can go in there and you can tell it which power mode to use. Because you could go medium, high, or low, or auto, and then start it. It also gives you information feedback as well when it's running. If you've done a mapping run, it'll tell you how long the cleaning run has got to go before it finishes, which is quite useful information. It's also, it'll also tell you when something's gone wrong. For example, if you've got a sock stuck in the brush bar or something, then you'll need to take some action. And actually, it'll show you a little video on the screen of what you need to do to clear the fault and then get it running again, which is great. For the home network, we can connect to Google or Alexa, and this is quite useful because if you're running the robot in your home and somebody comes to the door or something, you can say robot stop, and then it'll stop, and then you can go and deal with whoever's at the door, get your parcel or something, and then come back and then tell it to continue, which is again quite a nice feature for our users. Everything's got an app these days, okay? And our robot's got a great app. So you can, because the app gives you lots more control over the robot, and also, provides you with more information about what the robot is doing. We try to make this really easy. So even inside the box, when you open the box, there's a QR code you can read. You can get the download of the app. You can do the connection journey really quickly. We just use BLE to do the connection journey. So you take your phone close to the robot. The robot kills the power between the BLE power for security reasons, and then you can pass the credentials over, and then it's easy to connect your robot up. Once you've connected it up, you can send the robot out to do a clean. Okay, on the first run, it also does a kind of a scouting run. So it builds a map of the floor area in your home. It's basically an estate agent's view, 10 centimeters from the floor. You then get that onto the app, and then with your finger you can Dyson slice, so you can partition it up, and you can say, well, that's my hallway, that's my living room, that's my kitchen. You can also tell it what power mode you want to use to clean those different areas. You can also give it a time, so you might decide, well, actually, when I've gone off to college or something, then I'll start the clean at 9 in the morning, or 3 in the afternoon or something, and then it'll do all the cleaning while you're out of the house, which is great. And then it'll send you back a map of the clean that it's done, where it's been in your home, which is again quite useful because sometimes you've decided, well, I want to clean the whole floor area, but you may have closed the kitchen door or something, so the robot hasn't been able to get in there. Then you can say, well, actually, it didn't do that bit because I've left the door shut. So next time, I'll have to maybe I'll do another clean of the kitchen later. So the app is again really useful. Another important part of the robot is the mobility of the robot, right? Because it's got to get round your home. The reason some of the obstacles it finds is that people will have rugs in their home which can be quite thick, so we need to be able to get onto the rugs and get off them. People will have divides between different rooms, so again the robot needs to be able to get over these divides in order to gain access to all the areas in your home. Some people have, quite steps into things like laundry rooms and things like that to try and keep if there's any water sloshing around, to keep it in there. Again, the robot needs to be able to traverse those inwards and outwards. So we need a good traction system for that. Also, the designers need to think of when the robot is sitting on the dock, when we take the power away, that the robot doesn't relax and come off the charge contacts. So again, there's we need to give some thought into those kind of design aspects as well. So for the cleaning system, we've gone for a two-wheeled system, which allows us to move forward, move backward, and rotate. Okay. We've also got some jockey wheels here, just kind of beads, just to give it some stability, and also we've got the brush bar at the front, which is touching the floor. But again, there's a lot of design work that goes into the tyres. What material do we use for the tyre? What's the pitch and what's the depth of the teeth? All these things are kind of engineering decisions that we need to make for the robot to make sure we've got appropriate mobility around the home. Also, we've been able to put all the gears inside the wheel, so we're making most use of that space. So the gearing system is inside the wheel, and it's got a kind of a four-link actuation, so that when we're going over things, we're not tipping too high. We kind of try to glide over it a little bit. So that's a quick overview of the mobility of the system. For planning, so some of the things we've had to introduce. So because we've now got a D-shaped robot, we have to deal more with corners. So we'll go into the corner, and then we have to reverse out and then navigate around that. What's fantastic about round robots is that you can just go into a place, rotate on the spot, and then move on. You don't have to do this kind of reversing maneuver. So that's a complexity that's been introduced through having a D-shaped robot, which we didn't have for the circular robot. Our cleaning pattern is what we call an oil drop pattern, which is a square outward spiral. Okay, so the robot will start off and it'll do this square outward spiral. It's always moving one robot's width apart, which means that we're covering all the floor area and picking up all the dirt from the floor. So that's our kind of a primary cleaning pattern. We also have to do a kind of a traverse occasionally as well from one part to the other. If we're going back to the dock to get recharged, then we have to go from one point to another. Or if we feel we haven't cleaned all of a particular room, then we need to traverse from one part of the room to the other to finish that clean off as well. And for that, we use a kind of an A-star algorithm. So what we're doing here, if we want to go from the orange to the blue point, there's a number of routes we could take, and I'm showing here the red route and the blue route. The red route is shorter, but actually it's got a few more turns in it, and also it's a bit more complex because it's got to go through a narrow kind of gap. So if you give all these things, kind of a weighting, you can decide which is the best route for you to take. So the blue one has got less turns, it's a little bit longer, and it's not so dangerous. You're not going to risk getting caught between narrow gaps and things. So that might be the one that we would select for that traverse. We've got a load of sensors inside the robot. We're using IMUs. In my day, when I was your age, IMUs were quite big things, as big as your fist potentially. But they've been developed for use in mobile phone technology, which is fantastic. Using MEMS technology, you can have a fixed plate of silicon, and then a movable plate of silicon. And then what happens is, as it's moving, you're changing the capacitance between the two bits of silicon. And then using that, you can determine the acceleration, and then you can double integrate to get some distance, for example. So again, fantastic technology, and quite cheap as well. That you can get this for a couple of bucks these days for robotics. Developed for the mobile phone and made cheap. We've also got wheel encoders. So we've got Hall effect sensors on the traction system, so that we can determine how quickly we're turning. Are we having slip? Also, if you've got multiple Hall effect sensors, then you can determine, or at least multiple magnets, you can then determine which direction you're travelling in as well, which might be quite useful. So those are just some of the odometry sensors. But the 360 VisNav is the first robot that we've introduced which has got a dirt sensor on it. It's a technology that we've had in the stick vacs for a generation or so. So we introduced it to the robot. It's basically a piezoelectric. It's like a drum basically, and then any bits of dirt that hits it, we can count those, and then we can then predict how much dirt we're picking up from the carpet. At the moment, you'll get a map of that, a dirt map, back onto your app as well, so you can see where the dirtier areas of your home are. I think it gives you some satisfaction as well as a user that it's actually doing a good job and showing some intelligence. What I'm really keen for this technology is that we get into kind of closed loop cleaning, because now we know where the dirty areas is, then we can then decide, the robot can decide itself when it should go out and clean, and where it should clean in high power and where it should clean in low power. So that should be that's a really cool technology for the future. Another sensor that we use a lot, and again, I think this is fantastic technology, is time-of-flight sensors. Again, these were developed for mobile phones originally, so that when you put, a couple of generations ago, if you put your mobile phone up to your ear, the time-of-flight sensor could detect that you've done this, and then it could kill power to the screen to save power. But the technology's moved on quite a bit since that time. So basically, it's got an emitter which sends out through a pixel some pulses of light, and then there's then that's detected when it comes back, and it's timing the time of those photons in the air. And then if you know the speed of light in air, then you can calculate the distance from that. And it's all done on a chip, again, for a couple of bucks. It's just got an I2C connection to it, so fantastic technology. Excuse me. We've got a number of these in the robot. We've got 6 on the bottom of the robot, and this is our kind of drop system. Okay, so in people's homes, you don't want the robot dropping down the stairs because it's about 3.5 kilograms. It can do a lot of damage if it's flying down your stairs. So again, we've got detectors at the front, 2 at the back, and 2 at the side. In order to make sure that we don't drop down the stairs, or in fact that you might have other steps in your home as well that you don't want to traverse because they're too deep. So the robot's really safe in not falling downstairs. We've also got another set of sensors at the front, which are in a kind of a cross-sword arrangement. So as the robot is moving forward, if there's an object in front of it, it should detect the object, and then it can move back and take evasive action. It's got 2 long-range sensors which see about 2.5 meters either side of the robot. And then these are the sensors that, I mentioned earlier on this estate agent's view map of the world. It's these long-range sensors that build that up for us. I've also mentioned that we need to get close to the edge for cleaning. We've got an actuation system for edge cleaning. So we've also got wall follow sensors, one on either side, again to get us close to the edge to pick up the dirt as we're moving around the room. So those are just some of the time-of-flight sensors we've got on the robot. Okay, so again, as a roboticist, I'm sure you all know this, that there's no sensor that's perfect. Okay, so sensors always have their kind of vulnerabilities and scenarios in which they don't work. So we've got a bump system as well, and this is in 3 parts in the robot. The first part is we've got high fidelity bumps. So there's 5 switches at the bottom here, so that if we bump into something, we can detect where we've hit it on the floor. Okay, and then again we can take evasive action around that. We've also got a lower fidelity bump, which is basically there's 2 switches. You might not be able to see it, but if I push this, you can there's like a slight movement between the bottom of the robot and the top of the robot, and that engages a switch. There's a switch on this side and a switch on that side. So again, if we bump into a shelf or something, for example, with TV stands, they've sometimes got a shelf which is about the height of the robot. So if we hit that, then again we can take evasive action from that. Also, being a D-shaped robot, we can get into scenarios where we're turning into things. So also there's a switch on the side of each side of the robot. So if we rotate into something, then we can detect that and again take evasive action. Okay, so the robot gets its name from the 360 part anyway. The 360 part is because it's got a camera system that it uses for navigation. The camera system is an upward-facing camera, and it sees 360 degrees. It sees all the way around the room from 0 to 90 degrees. We only use about 0 to 45 degrees of that image, and that's what we use for navigation. We started off with the 360i. We couldn't get a fisheye lens at the time that would give us that kind of coverage or field of view. So we ended up making our own, which was really complicated. It had the top part had a diffraction, which then sent the light down to a mirror which was facing upwards inside the camera. So then the light was pushed upwards to another mirror, which then pushed the light down through a hole to get it onto the imager. Okay, so it was like it was 2 diffractions, 2 reflections, just to get the light onto the imager, which was quite complex. Also, the illumination system was separate. The illumination system we used was we used IR, and the IR LEDs were in the handle, and it would flood the room with IR when it was needed. In fact, but then we moved on to the developments in fisheye technology meant we could simplify quite a lot the system for the 360 Hurist and the 360 VisNav. So so now we've just got a single fisheye lens. In fact, there is a lens underneath as well, so it's two lenses effectively. So now 2 diffractions. We've got rid of the reflections in the design of the eye. And then what we do is the image we get is a polar coordinate image, and then what we do is we run it through an unraveling algorithm, which gives you this kind of rectilinear representation of the image. And then what we do is we pick out features from that. In fact, we're picking out kind of SIFT features, features in the image which are invariant to distance, so things like corners and things. And then we use those as features in our map. The robot has to work in in the start of the day where it may be dark, or the end of the day when it might be dark. So we've got an illumination system to help it in those environments. Sometimes the robot has to go underneath furniture and things where it's dark. So again, the illumination system helps with that. And in fact, we went for I quite like this system. It's using white light, and it's got 8 LEDs. And then it's got phase control for those LEDs, so we can have very, very fine control of the light coming out of the LEDs. And actually it looks really intelligent, because if it's going underneath a table or something, it'll put the front LEDs on to start with, and then as it goes underneath, all the LEDs will come on. And then as it's coming out, it'll switch off the ones that are coming out first, and then so it just looks quite cool the way it deals with the lighting. Just a quick look at the hardware and software architecture, because this might be of interest to you guys. It's split into 2 parts. We've got the low-level processing, which deals with the real-time aspects of the robot, and then we've got the high-level processing, which tends to deal with the high-frequency sensing, which is basically the camera, and also does all the assimilation of the data. So on the low-level platform, we use a TI chip, a system-on-chip device, which is basically, it uses an M4, again, an ARM processor, running at about 196 megahertz or something. And it does 2 things. It looks after the sensors, so it takes all the sensed information, then time stamps it so that we can send it up for assimilation in the HLP. It also takes commands from the HLP. So, for example, it's running 2 PID controllers, 1 for each wheel on the robot. The VAC motor and the brush bar motor have got their own microcontrollers, which are small M0s, or I think they might be M0 pluses actually, to control those 2 motors, and then the LLP just communicates with those to control them. There's lots of high power motors. The traction system is you can get your fingers caught and things like that. So there's lots of safety control functions in the robot, which puts some constraints on the hardware. So the hardware has to be single fault tolerant and things like that. And also part of the safety control functions are in software. So then we have Class B software, which is certified software that we use for dealing with the safety control functions. On the for the M4, we have an RTOS. I think we've moved over to free RTOS from Micrim recently, so that runs to give us some functionality, and then all the code that's written for on the low-level platform is written in C. On the HLP side, we have an Intel Cherry Trail processor. So this is the kind of a processor that you would have had in tablets maybe a generation or so ago. Okay, so it's a fairly powerful processor. It's got 4 Atom X5s running at 1.4 gigahertz, and I think it's got a boost frequency up to 1.9. We've also got a Wi-Fi chipset associated with it, which has got 2.4 and 5 gigahertz Wi-Fi. It's also got BLE for doing the connection journey and things like that. The Cherry Trail has also got a crypto core, so that all the software is signed, so the signature is tested before we start running the software, and also any software downloads are also signed and checked before we install them. The Cherry Trail also connects to the display, to the OLED display, and also to the touch screen, and it's also connected to the camera and the illumination. So that's a little bit about the architecture or the software on the HLP. So we're using Linux as an operating system, and then we've got all the software to do with the planning and the kind of navigation and that kind of infrastructure stuff, dealing with downloads and stuff, is all written in C++ by the software teams. Okay, so that takes us through a quick overview of what's inside the robots. There's one bit I've left off, which is to do with SLAM, simultaneous localization and map building, and I'm going to take the clock back to the 1990s when I was about your age, I guess. And I was just I'd been to Australia, and I was looking at decentralized systems, and the guys in Australia were just starting to look at these algorithms called SLAM, simultaneous localization and map building, which is really cool technology. Before that time, in robotics, you tended to be either doing localization, okay? So localization is somebody gives you a map, and then you go out with your robot and you build a small map, and then you try and say, well, actually, I think I'm here or here. I'll move a little bit further, get a bit more information, and then you can localize yourself in the map eventually. Or you're doing map building, okay? So some being kind of tells you where you are, so that might be GPS or something, and then with your sensors, then you can build up a map of the environment. And up to this time, there was kind of, you could do the two things the same way, but it was a bit ad hoc and not mathematically sound in some circumstances. But in around this time, people were starting to look at augmented state Kalman filters. So you'd have a Kalman filter which had all the features in your map and the vehicle in one state, and then an associated covariance to go with it. And this gave you that kind of mathematical soundness to bring in localization and map building together. So it was like fantastic technology. And this was just starting in, one of the research areas was in Sydney. And then I thought, right, I'm going to go back to the UK and I'm going to try and get this demo up and running of doing SLAM. So I went back to Bristol to the lab, and I got myself one of these Pioneer robots, which were quite popular, the red robot at the top there. And then I bought a laser rangefinder, which nearly blew my budget. It was about £3,000 at the time. It's just it's the blue box up there, so just as a laser scan of the environment. And then what I did in the lab, I made some poles as features, and painted them black, so I could put them down in known positions in the lab. And then what I could do is I could drive the robot around, and then it would do some scanning, and then it would build up a map, and it would use the map to localize itself in the room at the same time. And then the output is you can see the SLAM output there. The black crosses are where I put that's the true position, the ground truth of where I put the poles. The blue crosses are where this SLAM algorithm thinks they are, okay? The blue circles are to do with the uncertainty associated with that estimate of where the SLAM algorithm thinks the poles are. The red cross is where the algorithm thinks the robot is, and the red circle is the uncertainty associated with the robot. So that was my kind of first demonstration of that. I've put this ICRA because at the time there was a big competition. MIT wanted to call the technology CML, I think, concurrent mapping and localization, and then Sydney wanted to call it SLAM, simultaneous localization and map building. So there was like a very small, I think there was only about 15 people in the meeting in ICRA in about 2000 where this issue was discussed. And what happened was the SLAM won the day because, I mean, SLAM, you know, it rolls off the tongue nicely, which is one good thing. And also, I think the guy who was promoting, John Leonard, who was promoting CML, had been a student of Hewden White, who was promoting SLAM. So, you know, the supervisor took priority. So that just a little bit of a story about that. My own research in this area, what I wanted to do was, because I've been looking at decentralized systems, I was super keen to look at how you could do decentralized SLAM effectively. So what I did was, you know, there's the single platform, and then what I've done here is I've got 2 robots running at the same time, and you can see the outputs from that. So if you've got multiple robots doing SLAM, there's lots of benefits. You can make the map quicker because, you know, you're gathering more information. You become more certain. So for information that's shared, you're more certain about where the features are. So I was really interested in that technology. The other thing I was interested in was we made another robot. You can see it, the middle robot there, the middle image, which is it's got a white tower basically. And what I was trying to do here was, for areas where there were no features, I was trying to get a mobile platform to go in there and then become my feature. So, you know, so if there was an area without features, I could send these robots in, and then I could go and build a map of where they were, and then carry on the map building. Which was, again, really interesting research. It was great. My lab was on the top floor of this building, and I had some windows I could open, so I could actually go outside and do some testing outside as well. The beauty of that was that the inside, it was a floor like this, so it's like really smooth and things. But the floor outside was much more rough, and it had stones and things on there, so you know, it was a bit more challenging for the robot. So I could try building a map outside. I also thought, well, we had a van. Which we used to use for, you know, as a research centre. We used to use to go down to Maplins to get some bits of electronics, or to go to B&Q to get bits of mechanical stuff. You know, you could rent the van out. So what I thought I would do is I would rent the van out. We used to get lots of students in the summer into the research centre to help with our research. So I'd fill the back with students to gather the data and things. We made a board that we could put on top of the robot, on top of the van, which had the SICK sensor, the laser rangefinder. We put an odometry system on the wheel, and then we would drive around the site, and then we would build maps of the BA system site in Bristol, which was again super cool. Also, the UAVs that we started to build in Australia for doing decentralized investigations, we said, well, actually, we can use that for doing SLAM as well. So we added some extra sensors and stuff, and then we were able to do UAV decentralized SLAM as well. There was an interesting project called ANSWER, if anybody wants to have a look at that from back in the day. So that was then, and then I'll quickly go through some of the other bits because I've got how many minutes? 5-10 minutes left.
15 minutes.
Okay, right, yeah. But that's with questions, yeah. Okay, great, yeah. So meanwhile, in a lab in Oxford, Andrew Davison, Andy there, a great guy. He now is director of the Dyson robotics laboratory at Imperial College. Done some great stuff. Andy was starting to look at SLAM using a camera. Okay, so he was what he was doing was he was using the camera to. This is in one of the kitchen areas in Oxford at the time. So he's moving the camera around, and then this is the kind of output he's getting. He's picking out features which are the red and the yellow ellipsoid, and then you can get the camera position. So he's starting to do SLAM. You get ellipsoids to start with because, you know, a camera is really a good bearing sensor. Okay, but then as you move around and you get 2 bearings, then the uncertainty will shrink down towards it being a kind of a sphere or something. So Andy was doing this, which was fantastic work, and then some of the guys from Dyson saw this and thought, actually, you know, if we flip it looking upwards, this is going to be fantastic technology for the robot. But again, you know, it takes a while, right, to take research from, university and get it into a product. The core algorithm development. I love the SLAM algorithm. I love the elegance of it. Augmented state Kalman filter, extended Kalman filter, fantastic. But actually, we ended up with about 26 other algorithms that would make this thing work in people's homes, right? Because you need to decide, when do I add a feature? Because I don't want to add every feature, because if it's not a persistent feature, then it's just going to be noisy. Okay, so there's a filtering. If the map gets too large, because I'm adding loads of features as I'm moving around the house, then how do I deal with that? So how we dealt with it was we would start another map. Okay, so now I need to decide, when do I finish one map and when do I start another map? When I go back, how do I go from one map to another? Okay, so now I've got two maps. I need a portal to get through from one to the other. So our algorithms were, building up to make it work in people's homes. So there's a lot of work to do with that. There's also the camera and the illumination system, because we didn't have an appropriate camera. We had to go out and kind of build that. So that takes time and things as well, and the illumination system. Also, when you're putting a product together, you've got lots of other systems that you need to consider that you're bolting together, and all those have to come together to make the product as well. We have development cycles, so we have to get to a certain level of resolution, put something together, run that, learn from it, and then do another iteration. So, which again, we have to wait for other parts, because it's not just the navigation that we're putting into it. So that's why it took a lot, some time to get to launch. And of course, even when we've launched it, we still need to improve it through OTAs, because we're continually learning about the system. Okay, so what's happened since in SLAM? Okay, so I'm just going to quickly go in 5 minutes through some of these things, and then we can go into some questions. Again, Andy's works are fantastic. So he's now moved on from just using features, SIFT, just corners and things, embedding features, to using all the pixels in the image, right? And then what you get is a 3D reconstruction of your environment, which is, again, super cool. Needs lots of processing, needs lots of memory to hold it, but it's super cool. Super cool technology, and Tom Whelan did some great job on putting that together. But now that we've got this 3D representation, we can start thinking about objects, okay, which is, again, super cool. And in SLAM++, what we could do is we could take a model, say, of an IKEA chair or something, and then you could then say, well, actually, with this 3D map, I've got this IKEA chair, and it's in this position in the room. So that was really an interesting piece of work that the guys did for that. And then John McCormack, of course, deep neural networks were coming out at about in this era as well. So then you could use a deep neural network to take this 3D representation, and then you could, the network itself would tell you, well, that's a window, that's a bed, that's a bit of furniture, etc. And this is really useful for doing navigation in the home, because what you want to do is you want to pick out features that aren't going to move. So doorways, windows, fireplaces, and things that aren't going to move in your home are really good for navigation. You don't want to pick up, a child's toy or something like that, because that's going to move, right? Or even a chair. So pick out features that are going to be static. That makes the navigation a lot easier. And again, some great work from John McCormack on that. There was some work also, because I mentioned, we've got a lot of data to maintain. So again, I think there was a piece of work called Code SLAM. So what you could do, instead of representing it just as pixels, you had a piece of code which you could parameterize, and then that would represent part of that image, which is, again, really cool technology in order to shrink the amount of data that you've got. I'm really interested in this Gaussian belief propagation. So instead of having this kind of massive matrix and vector that you're maintaining, you can represent that as a graphical system. So you can get where the blue dots are, the robot positions, and one to the other. You can also use sensor constraints to pick out features as well. What I really like about this is that you can then have this graphical representation, but you don't have to process it all at the same rate. Okay, so I might have been in the hallway and then gone into the living room, and I'm still gathering data, but I can just update the bits in the living room where I am now, which is the important area, and then I can update the stuff. I can then pass the information down the network and process that more slowly. So I can then balance my processing load a little bit, which is super cool. Andy's also been, which again from my decentralized work is great, Andy's been looking at how you can use Gaussian belief propagation for multiple robots as well, sharing information, which I think is super cool. I haven't got much time to say much about that because I'm running out of time. They're also using Gaussian belief propagation for planning as well. There's two variants here. The non-GDP variants, if we're coming into a collision, then things have to slow down and change direction late on. Whereas by sharing information, you can get a much smoother transition. What's happening here is we've got vehicles moving from top to bottom and from left to right, and then we're trying to avoid collisions basically. And then in the GDP algorithm, we can just continue in a straight line because people have slowed down and sped up so that they don't have to change direction basically. And also the last, Andy's also looking at how we can use graphical methods or Bayesian processing in kind of neural networks as well. So there's some exciting work on that. Given time, I'll let you look at some of that work on Andy's website. Also, in Andy's lab, they're looking now towards as well manipulation. This is a demo I really like because it's reorientating things so it can pick up boxes and then put them in shelves. And then in a certain order just to make it look nice. What I really liked about it, because you see this pile of stuff that's just dumped on the table, and then they put it onto the shelf, and it looks really neat. And then when they finish, they take it back and put it exactly in the untidy state that it was to start with, which I thought was quite a cool part of the demo. Stephen James, fantastic, look up some of his stuff as well. He's been doing fantastic work on making discrete actions for learning. So you learn small bits of actions and then you stitch them together to do different things. I think that's quite an interesting technology, and Steve's done some great work on that. At Dyson. And then finally, my final slide, honestly, it's for autonomous robotics. A lot of the stuff that we're learning, I think, can be applied to sustainability. And I've just picked out two examples here. A blade bug is a robot which has got suckers on it, and then it can be used to go and help with wind farms, with the wind turbines, with the blades. If there's any damage on them or they need inspection, then the wind conditions have to be just right if you want to send a human out. But actually, if you can send a robot out in worse conditions, then it can carry on and do the work. So that's some interesting stuff. And then there's Qbot, which is a company that it's like a service company. And what they do is they come into your home and they can put a robot underneath your floorboards to put insulation on the underside of your floorboard, which is again some fantastic technology. Both of those have come out of Imperial College in London. Sorry, I've just overrun. I think so. I think hopefully we've got some time for some questions.
Yes. Thank you for that amazing talk. So we have. We have time for a few questions. So, is there anyone? Okay. So, yeah. So, can you catch it? So this is a microphone. Can you pass it? Yeah, maybe we can start with it.
Yeah. See if this works.
Hi.
How many people were involved in the design and for the software and hardware?
Okay, so it's it's a massive team because we engineer-wise, is at its peak, I think it's about 300, something like that, because we've got like a large software team, hardware team. You've got the quality teams, you've got the manufacturing teams. So at its peak, it was about that. And then you've also got massive teams that do, the advertisement, they put together videos and things for to support sales and things like that. So it's a fairly big team. Yeah.
Here.
Okay, sorry. Yeah.
No worries. Hi, Rob. Thank you very much for your talk. It
No,
was
that's great.
really
Great to be here.
exciting and even a bit touching because I got into robotics because of the SLAM problem.
Yes, yeah.
And I did my PhD at the Australian Centre for Field Robotics.
Fantastic. Yes, yeah, with Salah and
With Eduardo Nibot and Juan Nieto.
Oh, yes, yeah. I used to work with them years ago. Yeah, it's fantastic.
Nice.
Yeah.
So, as you said, SLAM has grown from just metric SLAM to semantic SLAM,
Yes, yeah.
even including moving objects.
Yes, yeah.
So I was wondering if you could give us your thoughts about how these new SLAM representations, metric, semantic, now even hierarchical SLAM, where you have objects and rooms and buildings, can be relevant for the cleaning problem.
Yes, yeah.
Or if it's relevant at all.
Oh, no, it is, yeah, that's right. I mean, there's interesting things like, again, with AI, how can AI help these SLAM algorithm? So things like, when you get loop closure, how do you do the actual closing? Because it can't be linear all the way around, because that probably isn't the way that it works, right? So I think, again, AI techniques that will help with deciding when you want to do loop closure and then how you do loop closure, to get, if you want to get straight edges on rooms and things like that. So I think AI may have a part to play on that, and some of the work that Andy's doing is looking at that area. Again, maybe the large language models as well may have an impact on on SLAM and how you might what's the best way of doing the cleaning? Maybe doing the spiral isn't the best pattern. Maybe given a room size, maybe there's a better way of doing it and things like that. So some of those technologies may come into that as well. So AI is definitely going to be interesting in that space. And nice to meet you. Yeah.
Any further question? Yeah. You can just throw it. Yeah.
Wait.
Hi.
Good catch.
Thanks. I was interested in when you were talking about next steps for the vacuum cleaner, and you talked about a kind of closed loop system looking at dirty areas of floor. So it's kind of a two-part question, sort of.
Yeah.
One is what are your plans going forward for this, but also I'm interested in more more unconstrained environments. So a vacuum cleaner is a two-dimensional problem fundamentally. So when's Dyson going to make a vacuum cleaner that can clean the stairs?
Yes. No, that's an interesting question. I'll start with the second question. In fact, I did. We had a fantastic event a few years ago. It was a hackathon event, so we got all the young graduates and the young, the interns in for 24 hours. We got loads of pizza in, we got loads of coffee in, and then we had 24 hours to come up with a device. So I went along and I suggested we do a step cleaning robot. So we did we took one of the docks, and then we could drive the robot onto the dock. Then the system would lift you up, rotate you, and then you could do the other part of the step. So it wasn't quite doing the full climbing, but it was at least doing a step. And it was a great event to get the students involved with that. Again, it's stair climbing is quite interesting, and how much are people willing to pay for something is also quite interesting, because actually you can just carry a robot up, or do you want to pay? I don't know, anybody here who researches quad robots? Because quads might be one way. Anybody? How much does a quad robot cost? Because if you wanted, do you know what I mean? Would you be willing to pay, I don't know how much a quad robot is, say £3,000 to get, for something that would carry or automatically carry up, or would you rather have this, that £3,000 in your pocket and then just carry the robot up, which might be quite interesting. And then for your next question, it's what's going to happen next in. I think in general, I think I haven't quite got my timelines right on it, but I think there will be robots in the home that can, which will have arms and things that will move around and can do things, more things in your home. But they're going to have to be more, they're going to have to be quite general in what they do to justify the cost, I think. So they might have to do, cleaning of bathrooms and things like that. They might have to be able to put, your shopping away, empty your dishwasher. They might have to do lots of things in order to justify the cost, I think.
Last question, Casper.
Yeah, I thought I was calling for Adrian here, but yeah,
Yes.
happy to ask a question.
Yes.
So thanks for the fantastic talk, first of all, and it's great to see how state-of-the-art technology is now turned into a product.
Yes, yeah, great, yeah.
But I was wondering about your sensors.
Yeah,
so
yeah.
on the one hand, you have the camera, which is a fantastic system and does a lot,
Yeah,
but
yeah.
still you seem to be relying on many other sensors.
Yes, yeah.
So I'm wondering, how much could you achieve with just the camera?
Yes, yeah.
And then while we're at it, also the other way around. I mean, the camera is an expensive thing. You need a lot of processing. That costs also money.
Yes, yeah.
Could you maybe think of a system that is much cheaper and would achieve a similar kind of job, but without the camera, just with the small sensors?
Yes, yeah.
Otherwise.
Yes, no, that's a great question. And actually, the sensors are kind of coming together a little bit because what was a point time of flight sensor, from ST a generation ago. They're now, I think the latest one, the 53L9, I think, is a 16 by 16. So you're kind of moving towards, having, camera. The two things are coming closer together. And actually, if you need, I think a camera. I think using vision is the way forward, I think, because and that's the reason why some of our competitors have been using LiDAR type sensors, but you're very limited with what once you've got that information, you're limited with what you can do. So I think having camera sensors is definitely the way to go, and then it opens the door to having semantics and stuff like that about the environment and stuff, which is very difficult to get with point sensors and stuff. So I think definitely camera's the way to go, and then I think you can get the cost off by using that camera in an intelligent way. Yeah. Good question. Yeah.
Last quick question.
Hi, I'm Matthew, coming in from Buckingham University, and
Hi.
my PhD is around object detection and artificial intelligence.
Okay, right. Yeah.
For the demonstration in terms of the sensors.
Yeah.
My question is more geared towards performance. I really thought it was a LiDAR system.
Yeah.
So my question is, I've heard that you make mention regarding like solid dust particles and that type of thing.
Yeah.
How would your detection sensors handle something like liquid or mushy stuff on the floor? How would it deal with a scenario?
Yes. So for small bits of if I put it in I'll give you the
Let's
extreme.
example, just
Yeah.
wee or poo or something like that.
Oh yes, yeah. No. There's. And
As you see my the
Oh no,
issues with
that's right. Yes, yeah. And there's lots of examples, of some of them are artificially fake, I guess, of robots that have gone through, various, jams and stuff, and spread it around the whole floor. So at the moment, if for this robot, if you drop a cup of water or something, it'll go over it and it won't affect it. It might make one of the effects is that the dust gets wet inside the bin, and then it becomes a bit like cement, so you have to then clean it off. But it wouldn't small amounts of dirt and stuff wouldn't affect it. Also, the sensors are quite good at if you get dirt on the say the time of flight sensors on the camera, then we've got detection systems for that. So it just then says, oh, I think you need to clean your robot, and then you take a cloth and then you wipe it off, and then you continue. Yeah.
Yes, thanks.
Great, yeah.
Thank you very much.
Okay, thanks so much.
Thanks, Rob.
Thanks,
So-
everybody.